This talk is about how to write the technical justification section of an observing proposal. It's intended both for an exercise during the DARA school if you have time, or as guidance for a real observing proposal. Almost every telescope that you might want to use in radio astronomy and elsewhere will have such a section, so you need to know how to write it to be effective. I'm assuming that you have a good science case as a starting point. So this talk is really about whether this observation is technically feasible with any telescope that you might have access to, and provided that it is, which instrument is best, what's the best setup of that instrument, does it give you the right resolution, the right sensitivity, the right spectral resolution, and how long do you need to observe for? Or alternatively, what noise level are you trying to attain? There's no point in trying to write a proposal if it turns out that you need to take several years to do the observation, and you need to find this out in advance. All observatories will require a technical justification in some form. Typically, it's a sheet of one sheet of paper on a proposal. It often requires the use of a specific tool to calculate the noise level of the observing time, sometimes also to do more sophisticated simulations. But there's plenty of help available. Each observatory will have a web page, and that gives you a starting point with access to documentation and tools. Very often, if you run into trouble when writing the technical justification section, there are help desks that will provide information to get you out of trouble. The most important thing to think about is the wavelength and sensitivity of your observation. So let's start with the wavelength. Sometimes you have no choice as to the wavelength at which you must observe. If you want to observe a specific spectral line at a specific velocity, then the wavelength is determined for you and you have no alternative. Sometimes, however, the choice is less obvious. You might have multiple transitions of the same molecule, for example, carbon monoxide, and it might make sense to pick a particular transition depending on observing conditions. In other cases, there may only be one type of line that you can use, and neutral hydrogen is an example. Continuum imaging is a bit trickier because you need to make a trade-off between the flux density and the sensitivity. The flux density of the target may vary quite a lot with wavelength, as may the sensitivity of your telescope. So you need to decide what's a sensible compromise between the two of those. Then you need to pick the spatial resolution you need. There's a simple relation, which I'm sure you've heard about, which relates the resolution that you get in radians to the wavelength of observation and the maximum baseline of the interferometer. The resolution is just lambda over d max. That then tells you the size of the telescope that you need to use, whether you're dealing with a compact array or something really large, like a VLBI array, which is the size of the planet. Then you need to think about spectral resolution and range. So if you're observing a spectral line, you'll need to work out what the full width of the line is and take some baseline on either side of it. If it's continuum, you're going to want to work out what bandwidth you need. And that will then tell you the number and width of spectral channels you need in your correlator setup. Then you go on to thinking about the field of view. The maximum scale of structure that you can observe with an interferometer is another lambda over d relation, but this time lambda over d min, where d min is the minimum space. And that gives you the maximum scale size of structure that you can observe with that particular configuration of the telescope. And you may want to pick a telescope configuration based on that number, depending on on what you want to do and whether the telescope is in fact reconfigurable, like ALMA or the VLA, for example. Then you need to look at the primary beam, which is the instantaneous field of view that you can observe. That's given by yet another lambda over d relation, this time with d being the size of the dish or in the case of an aperture array station. That then tells you whether you can observe your target in a single field or whether you need a mosaic of pointings to cover the whole field. Then if you're doing a statistical sample, you may need to compromise on the number of targets to observe. So you might want to observe a very large number of targets to get statistics, but that obviously puts your observing time up. So you need to think about that compromise. And then finally, you need to decide which array to use based on geographical location. Are your targets primarily in the north or in the south? And that will then set constraints because some targets are not visible from particular telescopes. So at the end of this exercise, you should end up with a short list of arrays that can do what you want and some rough ideas on the configuration and correlator setup that you need to do it. Then you need to think a bit harder about the sensitivity. The key parameter here is the surface brightness. So you need to decide first in your proposed observation, is your target going to be resolved into many beam elements or is it still a point source? If it's a point source, that's fine, just note the flux density that you expect. If it's resolved, you want to work out the surface brightness, and a simple rule of thumb for doing that is to take the total flux density, which we'll call S, and then the solid angle on the sky, omega, and the beam area, B. Work out SB over omega, that has units of Jansky per beam, and that essentially tells you how much flux density is coming from one beam element on a resolved source. And that's what you need for the sensitivity calculator. Where do you find these estimates? You can start from earlier observations. They might be lower resolution or sensitivity. Or you can start from theory. You might have a model of the source, which would tell you in principle what ought the flux density to be. It's important to know what bandwidth you need. That depends again on whether you're doing continuum or spectral line work. And this factors into the sensitivity because the RMS noise is proportional to the inverse square root of the bandwidth. So the bigger the bandwidth, the lower the noise level. All observatories will give you a sensitivity calculator to work out how long an observation you need, and I'll give you a list of links later. Once you use that calculator, you should know whether the observation is approximately feasible. So hopefully it comes out in a sensible time, minutes to hours, and not days or even years, which is more time than you would get in a typical proposal. If it doesn't work, then you may need to think about what you need to compromise. You may have picked too high a resolution, so the surface brightness has become very low and the integration time has gone up. You might have tried to observe too many targets in a statistical sample. You might have picked a bad frequency. It might be better maybe to go to a lower frequency if your source has more flux density at that frequency. And then finally, you might have picked the wrong array. It might be that the array that you really need is one in a different hemisphere. And so instead you should go and look at a target which is in the south or the north, depending on which telescope you're trying to use. So here are two example projects which we're looking at in the context of DARA. One is an extragalactic continuum project, one is a galactic spectral line one. So the top example is a bright quasar, 3C345. It's a double source, as you can see from the Merlin image in the top right-hand corner. And the purpose of a the exercise proposal is to work out whether it's a core jet source, so one of those components is actually the core, or it's a gravitational lens, so that you have two images of the same object next to each other. And one of the ways that you can do that is to observe at different frequencies. If it's a gravitational lens, then the two images should have the same flux density same flux density ratio at all frequencies. If it's a core jet source, then you would expect the core to have a much flatter spectrum than the jet. And so you can do spectral index imaging to work that out. Or you can resolve the source in more detail because you expect the core to stay compact as you increase the resolution, but the jet will resolve out. The alternative is the star-forming region maser project. So this is looking at maser emission from methanol in a star-forming region. The top two panels are the integrated spectra taken with a single dish showing the various maser lines, and the two options that you're trying to distinguish. The left-hand example is an outflow with red-shifted and blue-shifted masers. The right-hand example is a set of masers in a disk, and what you can see there is masers outlining a ring of emission around the central star. And so to distinguish between those possibilities, you need spatial resolution, and so the project is to look at spectral line VLBI at the methanol frequency, or transitions at other frequencies in different bands. Now, as I promised, is a list of example links. Obviously, I won't go through these, but they're here for your reference later. What I've tried to list here is for each telescope, at least a reference to an introduction to observing with a telescope, a link to the sensitivity calculator for that telescope, and a link to the archive where you can get old telescope data and have a look at the type of data that, that you can get with that machine, either for your own source or for related targets. In one case, I've also put a link to the simulator, and I'll come back to that in a minute. This is not an exhaustive list. Obviously, there are many other telescopes which have similar setups, but these are perhaps the most interesting ones for the purposes of the Dara School. Now we'll go on to a few subtler things to think about. You've got the basics of your proposal sorted out, but there are a few more things that you need to know in case of subtleties. So the first group of points is about calibration. Very often, the observatory will come up with a calibration strategy for you, but in other cases, they won't. And in any case, it's a good idea to understand what the right calibration strategy is for your observation. You need to know which calibrators to observe and how often to observe them. So, for example, you'll need to think about the absolute flux scale. So you'll need to observe a primary flux calibrator. You'll need to calibrate the bandpass of your telescope, and you'll need to calibrate the complex gain, the variation of amplitude and phase across the target. And so that will require a relatively nearby source in the cases that you use that. And so again, observatories provide tools to help you here. They'll provide lists of calibrators and standard calibration. Sometimes the observatory will find the calibrators for you and build the observing program. But one other thing that's useful to know at the proposal stage is whether you can self-calibrate. The reason for this is that if you can, it often reduces your calibration overhead by a lot. And so that you can adjust your observing strategy and your overheads based on that. And talking about overheads, this is something that people often forget in writing technical justifications, the amount of time that you've calculated with the sensitivity calculator will be the time on your target, but you also need to include the time for calibration and the time needed, if it's appropriate, to slew the telescope between target and calibrator. And so 30% overheads are not unusual in some cases. Then another group of points concerns imaging and whether the interferometer and the length of an observation is appropriate to making an image of the quality that you need. And so this comes down to how complex the field is compared with the coverage that the telescope provides. You need to decide whether you need a long track or a short snapshot to do the imaging that you need. Sometimes you will need to combine arrays or configurations, so two entirely different telescope observations, or more likely different configurations of a reconfigurable array like ALMA or the VLA. You may need that to get a combination of surface brightness sensitivity and resolution. Some arrays actually have simulation tools to help you here, so you can make a model of the source from theory or guessed from earlier observations, and you can predict the image for realistic noise and calibration errors. ALMA has rather a nice tool, which is one of the links on the previous slide. And then finally, some special considerations depending on the type of observation that you have in mind. One is calibration for polarization, which isn't always included in the standard procedures. You need to work out whether you can calibrate the polarization accurately. That sometimes requires extra calibrations and an extended observation. You might want to look at a special observing mode, high time resolution, or solar or something like that. So that has its own considerations. You may have time constraints. For example, if you're trying to observe simultaneously with a satellite observation of the same object, you may be constrained as to when you can do that. You may want to observe a target of opportunity. For example, some telescopes will give you time to trigger when a particular object goes into outburst, and there are special considerations to do with that. And then sometimes you need additional calibration for special purposes. One obvious example of that is when you want to do precise astrometry of your target and get its absolute position as well as possible. And then finally, there's a set of less tangible things that it's worth thinking about when you put in your proposal. Of course, solar arrays are in bigger demand than others. Sometimes you can get oversubscriptions of 10 to 1, and getting time is highly competitive. If you can do the observation with a less oversubscribed array, it sometimes helps to do so. But even within a single telescope proposal, you need to think about what targets to observe. Sometimes the oversubscription varies a lot depending on the hour angle of the object, the right ascension of the object. So maybe the galactic plane is very popular, or conversely, maybe out of the galactic plane is very popular. And so you can look at the statistics of oversubscription for particular array configurations and positions in the sky, and adjust your proposal to make best use of that. Then another problem, which is particularly acute at very low and very high frequencies, is whether the project can be only scheduled in really good weather. So for very high frequency observations, you need low water vapor column and very stable troposphere. Conversely, for low frequency observations, you need stable ionosphere, which is almost always at night time. And some of the projects might be very demanding. That means that they're harder to schedule, and it's sometimes worth thinking about whether this is actually what you really want and whether you should move to a lower or higher frequency in order to make the observation easier to do. You can check all of these things on the telescope website, along with a lot more information help you write proposals. So thank you for listening, and I'll stop there.